All right, so we're going to go over, I should say, some more optimization questions. The questions I promised to give you guys earlier today in lecture. I just want to remark back here, though, we want to get rid of these here. Okay, so that the maximum area here for that earlier question is found by taking this square with dimensions square root of 2 by square root of 2. And of course, when you multiply those, you get the square root of 4, which is 2, so that the maximum area inside that unit circle is in fact 2. We misreported earlier that it was 8, so I'm going to go back here and just say nope. That maximum area when you have a unit circle is in fact 2. Okay, just to let you guys know, go through that correction there. Okay, now if we change the question in this way where you have an ellipse as opposed to a circle here, it has the same format in that we're going to let, with this point x, this distance here, is now x. So we're saying this length here is x. The length of that rectangle, though, the total length, will be 2x. And maybe it's helpful just to change that kind of color and say, hey, this is going to be a distance x, so this is 2x. And similarly, this distance is y, because that's the ordered pair there. You have this x coordinate and this y coordinate. So I guess I've highlighted the wrong thing. Here's the y coordinate. So this distance is y, so you're looking at the total distance here being 2y. So there's the dimension here. So that the area of this rectangle, we want to find the largest area. Find the area of the largest rectangle that can be inscribed inside of the ellipse. So that'll be 2x times 2y, again, where x is positive and y is positive. That's an important detail. We're not going to get negative area. But then you get area becomes 4xy. So we want to get a handle on having a function of a single variable. This is a function of two variables. It's a function of x and y, these two values here. So what I'll say is go to the original ellipse here and you solve this ellipse for y. And what that'll do is that will give you, if we take what's called the positive solution up here, we're going to take that positive y solution, the top portion here. But we have to solve that equation here. So if we subtract the x squared over 16, let's put this maybe over here. So we have y squared over 9 becomes 1 minus x squared over 16. And that gives you y squared equals 9 times 1 minus x squared over 16. So y will be plus or minus square root 9 times 1 minus x squared over 16. Now we're going to do some simplification here. I'm going to write 16 over 16 to represent that number 1. And I guess I'll factor out the 16. So I get 9 over 16 now times 1 minus x squared. We're factoring out the 16 in the denominator. Right, it's a common term there. Now, what that'll do for us is by the product rule now, square root of 9 over 16, square root of 1 minus x squared, and the square root of 9 over 16 becomes 3/4 square root of 1 minus x squared. So that meant two things here. Right, that means y is 3/4 square root of 1 minus x squared. That's the positive answer. And we have the negative answer. So the positive, and I guess I'll change colors here. This is the positive answer for y, the positive y coordinate, and the negative. So remember what we said. We're going to use the positive here, so we change that color. This is the top portion of the curve of an ellipse because you have a relation. There's the bottom portion, and we're saying we're going to use the y coordinate value being positive here. So we're going to use the top portion of that curve. This is the top portion in yellow, orange, whatever you want to call it. So we're going to use this. We're not going to use the negative y values. So y is 3/4 square root 1 minus x squared. So this is my y here. This is what we plug in here for y. So you say that was 3/4 square root 1 minus x squared. So altogether we have this area here formula. So I'll copy that. What this means is 4x times 3/4 square root of 1 minus x squared. It looks like our 4's cancel, so that the area formula is 3x square root 1 minus x squared. So this is going to be what we use here. This is what we want to optimize this. Okay, so that's the idea. To optimize that function, which really means to find the relative max, relative min, sign analysis on the first derivative. So this is an area formula for the rectangle. So if they want the dimensions for the maximum area, it's going to give you a relative max, guaranteed. Guaranteed to be a relative max. Okay, so we need a derivative. So that's the idea, is to optimize. And when you take this derivative now, you notice you're going to get, or you're going to have to use product rule. So we have 1 minus x squared to the 1/2 plus 1 minus x squared to the 1/2 times that derivative of 3x. So we'll use product rule now. This is 1/2 1 minus x squared to the minus 1/2 times a negative 2x by that chain rule. This derivative is a lot easier. It's just 3. A prime x. Notice your 2's cancel. So we're going to get negative 3x times, and I think, yeah, let me double check here. We're okay. Yeah, we should be okay. Negative 3x times here, let's be careful. And then it'll be plus 3 times 1 minus x squared to the 1/2. And as you guys know, I do not like to have my term start with a negative term. So I'm going to have to find critical values here for this, but we're going to have to factor out the greatest common factor. So it's 3 times 1 minus x squared to the minus 1/2, the smallest power. And that's just going to leave us with a 1 minus x squared here when we divide. And it looks like that's going to be there should be an x squared here. Yes. There was something bothering me. Squared, squared. This is the x squared. Here's what I want to remark. X and x gives you that x squared. So there we go. Okay. So get 3, 1 minus x squared to the minus 1/2 now. 1 minus 2x squared. So altogether, 1 minus 2x squared over 3 minus x squared to the 1/2 power. Now this is my derivative here. Okay. Okay, now go back and remember a few things about this. X and Y are positive. Now, when I go back to this function here for A here, again, the domain of this function is the values of X that are between -1 and +1. Because we have a square root of 1 minus x squared here. Okay, so you can use sign analysis and find where this thing should be greater than or equal to 0. You're going to find it at -1, +1, and everything in between. So there's my domain. So I already say, okay, I have that domain here. Finding critical values, that numerator. We set the numerator equal to 0, solve for x. So we get 2x squared is 1. X squared is 1/2. X is plus or minus square root of 1/2. So x would be plus or minus 1 over the square root of 2. Remember, x is positive. We're going to use positive values. So here's an x value for my critical values. And again, similarly to what we had this morning as well, we set that denominator equal to 0. And this is where that derivative does not exist. And you say, okay, 3 times 1 minus x squared to the 1/2 power is 0, which means 1 minus x squared to the 1/2 power is 0. Or 1 minus x squared is 0. X squared is 1. X is plus or minus the square root of 1, which is 1. So remember, you have two solutions here, but we're only going to deal with the positive values. So we throw out the negative value, and here's another critical value. So we have two critical values here. So for the sign analysis portion, just like earlier today, you're going to go from 0 really to 1. That's a prime x. At 1, the derivative does not exist. At 1 over the square root of 2, the derivative is 0 here. So again, we have regions 1, region 2 to perform your sign analysis on. And if you guys remember, 1 over the square root of 2 is the same as the square root of 2 over 2, which is about 0.7. You know, if you guys remember from trigonometry, that's a very famous ratio. It's like 0.707. So it's good to know that ratio because I'm going to use again 0.5 as a test point and maybe 0.8 as a test point for my sign analysis. So we go back to that derivative. Now the denominator is going to be positive here always. Doesn't matter. So it's the numerator again that's going to contribute. Okay, you say, why is that denominator going to be positive? Because for all of these values here of x, that radical, the square root of the denominator, has to be a real number. And the only way it'll be a real number is if it's positive. So we plug in the test point of 0.5 here, and then also, again, 0.8 for that first derivative. We're going to go to the TI. 1 minus the 0.5, and I forgot there's a 2, so we'll put the 2, times 0.5 squared. We notice we're going to get a positive number. So at 0.5, that derivative is, in fact, positive. So region 1 is positive. So that's what we're going to label that. So now, for 0.8, the test point, 1 minus 2 times 0.8 squared will give you a negative answer. We don't care about the value, we just care about the sign of the value there. It's the test point. So you have increasing decreasing situation. So sure enough, remember this function represents area. And sign analysis on that first derivative for the area here, right? It's going to give us the location of a relative max. So that means A max is the relative max. It has a relative max at A of 1 over the square root of 2. Now that's the maximum area for a rectangle, because the area here is for a rectangle here. But the question is, what are the dimensions? They didn't really ask for the relative max. They didn't really ask for the maximum area. They said, what is the dimensions of that rectangle? Okay, now this is an x value. So remember how we set this all up. You have a length here. If I go back, length and width. So my length is 2x right in here. So I'm going to get rid of some of these highlighting. And to say to you, if we kind of think of it this way here, right? This is my 2x. This is my length of my rectangle. So I can say that that length would be 2, and I think x was, what was x? 1 over the square root of 2. Is that right? Yeah, it's 1 over the square root of 2. I apologize. So this is my x value. So that length really becomes 2 over the square root of 2, but when we rationalize the denominator, you get 2 square root of 2 over 2 for the length, and I was correct to begin with that my length here is really the square root of 2. So this is the dimensions for the length here. Okay, so the width portion though, you know, what's the width now? The width is 2y. So I guess I'm going to get out the purple here. 2y for the width. So we say w is 2y. So if I say to you, here's my width, it's 2y. Well, remember what y was. Right, where's our y value? Here we go. 3/4 square root of 1 minus x squared. So width will be 2 times that 3/4 square root of 1 minus the value of x was the square root of 2, right? What was 1 over the square root of 2 squared. Okay, I want to move things out of the way here. So remember, this is my 3/4 there. I'm going to try to move it. Okay, here's the y value. Guess we colored it purple. I don't know. Here's y. So things y. So things y. So the width becomes 3/2 now, square root 1 minus 1/2, 2/2, 3/2, square root of 1 minus square root of 1/2, which will be 3/2 1 over the square root of 2, and we rationalize that denominator. So this will be 3 times the square root of 2 over 2 times 2, which is 4. So here's my width, ladies and gentlemen. So we have the dimensions now. Length was going to be found it up here. Square root of 2. Copy that. Paste that. So, note, this is a rectangle. This is the maximum area rectangle here. So my length is the square root of 2, and the width is 3 square root of 2 over 4, by the way. This is the dimensions. So the area would be found if I multiply length times width. They didn't ask for that. So square root of 2 times square root of 2 is square root of 4, and that's going to be a 2 then. Okay. And so it looks like my maximum area will be a 3/2 in this case. So just kind of throw that out. They didn't ask for that, but going to give you that. They did ask for just simply the dimensions. So here's your length, here's your width, ladies and gentlemen, for this optimization question. And maybe you want to do a nicer area. This is the one I promised you guys. The second one I promised you guys is this boat dock question that, a boat leaves the dock at 2 p.m. So, all right. You got a boat leaving the dock and it's traveling south at a rate of 20 kilometers per hour. Right? So I started to set this stuff up. So remember, distance is rate times time. They gave us a rate, and the rate they gave us was 20 kilometers per hour, but it's going south. So I put a little compass here, and that's the distance d that we found earlier, saying d is 20 times t. So we're going to really say that this distance is down here, 20t. But if I plot this on a Cartesian coordinate system simultaneously, meaning this is an x and y axis, it's going to be consistent with looking at this as a north, south, east, and west. The location of that boat in terms of x and y coordinates is 0, negative 20t. So this is like the x and y coordinate there. Okay. And that's the distance that that boat traveled. Distance is rate times time, so it's 20t. And this is time. You say, what do you mean time? This is t is actually time. Okay, and you say time really after 2 p.m. So it's like your stopwatch starts at 2. So t is time after 2 p.m. Okay, that's the time variable. And they say another boat has been heading due east at 15 kilometers per hour. So the east boat has its rate. So the rate here for the east boat is 15 kilometers per hour. So we say, okay, here's that 15 kilometers per hour. All right. And it reaches the dock at 3 p.m. So it reaches this dock here, the starting point, an hour later, really. So you say, okay, how long did it travel in 1 hour? Well, it traveled 15 kilometers. So here's why we represent that distance here. If it is at this location an hour ago, and then it sails for 1 whole hour at 2 to 3 p.m., it's now at the dock. This is where the dock is. So it had to have started at this location. And you say, what's that location? That location is minus 15. At least on the Cartesian coordinate system. So it starts here at minus 15, but the distance it traveled in 1 hour, will be, let's get out our purple, rate times time. This is the 15t here. So we just found this is the distance that it traveled, but it started at negative 15 because it's now at the dock. So this is the location now in terms of an x and y coordinate. It's your location of that starting point for the second boat. And this is what I'm referring to. So we're working with the coordinates, the x and y coordinates of this. So what they're going to say now is at what time t are the two boats closest together? Now, what I wrote earlier today, the distance between the two boats is right in here. This is the distance. It's this horizontal line. Sorry, diagonal line. That's the distance between the two boats. Okay, and so if you see this, you say, well, that's interesting. That forms a right triangle. I wonder if that has anything to do with what we're going to do. And the answer is yes, it does. They want that shortest distance kind of thing. At what time t are the two boats closest together? That's a shortest distance kind of question. So shortest distance. Now, there seems to be a couple of ways we can do this. We can use the distance formula again, or we can use Pythagorean theorem, but the distance formula, we're going to get square root of. Now remember, how do you want to do this? First point, second point, right? Remember, this is the distance formula. x2 minus x1 squared plus y2 minus y2 squared, or you can use Pythagorean theorem. Okay, because it's really going to be the same thing. We could say d squared then by Pythagorean theorem is going to be negative 15 plus 15 squared plus this 20 squared, or you can say negative 20 squared there. Doesn't matter, it's going to be positive. So we can use the distance formula since it has coordinates, or we can use, you can use either. If you use Pythagorean theorem, I apologize. Pythagorean theorem was negative 15t plus a positive 20t squared. And this is by Pythagorean theorem because our distances are positive. Okay? And this is what I'm referring to. This is the distance for both. And this will be squared. All right. Let's just do a little bit of simplification. So d squared will be now, I'm going to start this out and change my terms, 400t squared now plus, and then I'm going to put this 15t minus 15 squared here. So this is by your Pythagorean theorem, looking at it as a triangle, or we can use the distance formula. It'll come out to be the same thing. Similar thing. So this is my distance. Now what I'm going to do now is this. I'm going to call this here d squared. I'm going to call this f of t. I'm going to change that into a function. So f of t is 400t squared plus 15t minus 15 squared. And now you have a function of a single variable, time t. We want to optimize this. Sign analysis, or find the relative max or relative min. Now it's going to be shortest time, shortest t, smallest t. So it's going to be a minimum value. You're not going to ever get a maximum value. You're going to get a minimum value. So sign analysis is going to reveal that this is 800t, getting that first derivative, finding the critical values. Don't forget by chain rule. So I'm going to take that derivative. 800t plus 30 times 15t minus 15. So my first derivative becomes 800t plus, now 30 times 15, if you guys remember what 30 times 15 is, 300, that's 450, minus 450 if we distribute this. So this first derivative is 800 plus 450. 1250t minus 450. So here is my derivative. We need critical values. So set this equal to 0. You get 1250t minus 450 is 0, which means 1250t will equal 450, or t will be 450 over 1250. Okay, now we can simplify this, but I think I'm going to look at the numerical answer. We're going to go to the TI now. 450 divided by 1250, and as a time value here, this is t, which is 0.36. Now you say, what is this? This is 0.36 of an hour. Okay, 0.36 of an hour. We found the time here. Now that's kind of useful information. Notice this though. We said we're doing sign analysis. Time is going to start at 0. You start your clock. Remember, 0 is when it was 2 p.m. My critical value, that derivative, f prime t, is 0. So we have two regions. So I guess if I said, 0.25 here for a test point, and maybe 0.5 for a test point, that would be some good test point candidates for that first derivative. So I'm going to plug in these two values into that first derivative, and the first derivative is right up here, so it's 0.25. I'll put that on top, and then 0.5. We're going to plug that in there. But we're going to plug it in the TI, so you get 1250 times 0.25 minus 450 in that first derivative. And we get a negative value. So what that means is region 1 is negative. Okay, we got a negative value there. 1250 now times the 0.5 minus 450, you're going to get a positive value now. So we have region 2 is nice and positive. So what this means here, remember, for sign analysis on the first derivative, you got the time in which that distance is decreasing and then the distance is increasing. So here, if you're standing here, oops, let's get the right color, you're at a relative min. And that's a time value. So we have a relative min for the distance function. The relative min is at f of 0.36. That's the relative, sort of distance there. Minimum distance. If you go back and you say, well, what are they asking for? Right? They're asking at what time are the two boats here closest together. So they're asking for what t did you have that minimum distance relative, closest together. At what time t when you started at 2 p.m. So at what time and you started at 2 p.m.? Well, we know we started at 2 p.m. right? But at 0.36 of an hour, we're at the closest distance. We're at the relative min. At this time, we're at the closest distance now. But that's not a time value. So we're going to have to convert 0.36 of an hour to minutes. Okay. 0.36 of 1 hour. Convert that to minutes. There's 1 hour for every 60 minutes. So your hour is going to cancel. So as a time value now, 0.36 times 60 gives you 21.6 minutes, ladies and gentlemen. Okay. So this is 21.6 minutes. That's after 2. So you can say, is it 2? It's 2:21, but we still have this idea here of 0.6 minutes. So 21, remember what 21 and 0.6 minutes means. It's 21 minutes plus 0.6 of a minute. So we're going to have to convert again now here. We're going to convert the 0.6 minutes. And you say, well, how do I convert 0.6 minutes? You're going to take the 0.6 minutes, and you're going to remember that for every 1 minute, you have 60 seconds, so that your minutes cancel. And so if we multiply 0.6 times 60 now, you get 36, ladies and gentlemen, and that's 36 seconds, because these are my new units there. Just like up here, we're in minutes now when we converted. So here's what this means. 21 minutes and 36 seconds later, after 2 p.m., you have the closest distance. So you started at 2, and 21 minutes and 36 seconds later, here's the time. 2:21, 36 minutes and seconds. So at 2:21, 36 minutes and seconds, and ladies and gentlemen, that's what they want you to do here. You found the time where the two boats were the closest. Anyway. All right. So I said I'd get you guys some of these questions up and running today, and I did, and I'll send you guys an announcement in Canvas, and I hope you guys enjoy the demonstration. Take care, stay safe, have a wonderful weekend, and we'll see you guys later.